So this was the picture that I was trying to paste in the lecture yesterday, but it was for some reason the paste functionality was not working as we wanted it. So anyway, we have proved in the last class that plus delta rather, let me put this in the next line. On the picture here, plus f plus fc plus kf. Fine. This beast, and we had also drawn this picture. I'll try to paste that. So trying to paste this from the yesterday's lecture. And yeah, let's forget about this. I'll draw that again. Let's forget about pasting here. F this is FC. This is minus FC. This is FC. There's a pulse here. 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 Another pulse here. Another pulse here. I'll draw the positive half. The negative half will be symmetric. J0 beta, J1 beta, J2 beta, J. Fine. FC plus FM, FC plus 2FM, FC plus M. FM. Fine, this is what we did yesterday. So the FM spectrum ideally has infinite number of sidebands and an bandwidth. The relative strength or the strength of these sidebands by JK beta. Fine. So now let us discuss certain properties of. It's not allowing me to go left from here. So maybe what I will do is I'll simply erase this because this is available in yesterday's lecture. So I will erase this picture. Or I will.
Sir, I am not able to see your screen.
Okay. Okay, Niharika, just hold on a second. Now can you see the screen? Niharika?
Yes, sir.
Okay. So I'll just move this picture over here to give us some space. Yeah, so this gives us enough space. So now let us look at some properties of this Bessel's function or some properties of Bessel function. Some Bessel function. 1 jk beta equal to -1 to the power k jk or j of minus k beta. Fine, this is an odd function in k, or this is how it behaves for k, or summation k goes from -infinity to infinity jk square beta equals 1, which means the power contained within all sidebands signal is fixed. Fine. And for small beta, one, I'll just write it down here. Minus j minus 1 beta equals beta by 2. This you can see from the plot. This is j1 beta. And this is for small values of beta, this is close to beta by 2. Then I'll use the red one. Close to. Then the third property is, see, up to 1. So till up to 1, J2 beta, J3 beta are all approximately Jn beta in this region, approximately 0 for n greater than 2. Fine. So in general, also observe that Jn beta becomes significant only after beta. See, J1 beta becomes significant earlier. J2 beta, if you look at it, becomes significant only around n beta equals 2. J3 beta becomes significant around beta equals 3, and so on. So you agree with this observation? And in general, Jk beta represents the strength of the kth sideband. Jk square beta represents the power contained within kth sideband. And this makes this implies that J0 beta is the strength carrier and J0 square beta is the power contained in the carrier component for a modulation index beta. And since there are certain points where the Bessel function crosses 0, since there are where K beta crosses 0 for all sidebands, not all carrier components, for all sidebands, there are certain values of beta for which the contribution of a carrier is 0. Fine. So these points say this is, oh, sorry, this is close to this is close to 2.25 approximately by the looks of it. Yeah, 2.4, 2.3, 2.4. So this is the one node crashed. This is the point where the carrier component, for example, I'll write. So for example, the contribution, the carrier becomes 0 when beta. Fine. So there are signal, and that is by making the carrier component 0. And we have already seen that in case of narrowband FM, or when beta is small, it corresponds to that we have seen. Fine. So as a concluding remark to this discussion, the theoretical bandwidth FM signal is infinite, but the number of significant sidebands used detect or approximate the usable in general for rating signal with a maximum frequency FM f small f subscript m bandwidth is fine. This is called the Carson's rule. Fine. Any questions till now? Guys, any questions with this? Any problems with this? So since you guys do not have any questions till now, let us move on to the next part. Analyzed an FM signal. Now, question is how to generate in case of FM, the frequency Fi output is a function of the voltage, the message signal therefore therefore need system an oscillator whose frequency can be controlled via an okay, this is misbehaving today slightly. No problems. Yeah. Externally via an externally applied voltage. We call such a setup a voltage controlled you have heard of the term voltage controlled oscillator earlier? Guys, have you heard this term before? Voltage controlled oscillator in some other course? I take that as a no. That said, hold on a second. So since OneNote is misbehaving today, let's move to whiteboard. So let's move to, we're just moving to whiteboard because OneNote is misbehaving. I'll close OneNote, save this, save the whiteboard file as an SVG file in the folder. I'll point it to you. The only problem with whiteboard is that we do not get to export files as easily as in OneNote, but this is less prone to crashes. or less misbehaving. So I'll continue where we picked off. So I'll okay, hold on. Create a new whiteboard. Fine. So yes. Now VCO is an oscillator whose frequency is controlled via an applied voltage. Fine. So to draw a VCO, let's first draw an oscillator. This is an LC oscillator. Right? This is an LC oscillator with an oscillation frequency 1 by 2 pi root LC. This is the L Henry, and this is capacitor with the capacitance of C farad hertz. Fine. You any problems with this? This is you have studied this oscillator? Bhaskar, Bhaskar, you have studied this oscillator? Bhaskar? Okay. Pavan?
A basic LC oscillator we studied, sir, but
Yeah.
not.
No, obviously not the voltage controlled oscillator. That's what I'll be spending time on now.
Yes.
Basic LC controlled oscillator, basic LC oscillator you have studied, right? Now, do you know what is a what is a vector? Do you know what is a varactor diode or a varicap diode? Pavan, heard of this thing? Devices course. No. Okay. Strange. So consider a PN junction diode. Reverse bias. So I'm not that good with devices, Correct me wherever I am wrong. So this is P, this is N, and I apply negative voltage here, positive voltage here, and the negative charge carriers accumulate here, and the positive charge carriers, or the positive charge carriers accumulate here, and the negative charge carriers slightly thickening it actually stops this dot effect. Good. Yeah. So positive charge carriers accumulate here, and sorry, negative charge carriers accumulate here, and positive charge carriers accumulate here, and consequently, these are what we call naked charges. Fine. Fine. Feedback. Abesh, this is fine. Badly drawn, but Ashwin.
Yes, sir.
Yeah. So this now, as I increase the reverse bias, the width of region, the width of the depletion region increases, right? If we look at the depletion region, fine. Any questions with this? So my turn of questions. What is this?
Like a capacitor.
This is a capacitor. Yes. Yes. So this is like a capacitor. So you have heard of the term parasitic capacitances? Who is calling me? Just a second. Hold on. I'm getting a phone call. Sounds important. Yeah, sorry. So this is like a capacitor. So you have heard of the term, Yash? Have you heard of the term parasitic capacitances? In you have VLSI circuit design this semester? Yes.
I have not heard of the term, sir.
Okay. Do you have the course on VLSI circuit design this semester? Idiot is paddling again.
No, only embedded systems, not PLS.
Yeah. Yes. So sorry for the interruption. So do you have a course on VLSI design this semester? Yes.
No, sir. There is
Okay.
only embedded systems.
Okay. There is only embedded systems. Great. So whenever you have a course on VLSI design, you will come across this term parasitic capacitance. So whenever there is a reverse bias or wherever there is a PN junction, there is a capacitance associated. So like in case of you know light emitting diodes, right? Light emitting diode, Zener diode, you have done all of this or no?
Yes, sir.
Yeah. So in a Zener diode, we use the voltage limiting property of a diode to our advantage and use it as limiting the use it for limiting the voltage uh, across any circuit. Similarly, in case of uh, a light emitting diode, we use the fact that recombination in the forward bias causes the release of a photon. We use that to our advantage. Similarly, we to exploit this variable. So by increasing the reverse bias voltage, we can increase the charge as well as the width, the depletion region, and hence control the capacitance agreed. Yes.
Yes, sir.
Yeah. Now for this discussion, if you do a course on devices or if you study this in devices, you will develop better mathematical models. I know very less about devices. So we, I'll simply say that we can approximate the capacitance of a varactor diode as CT in equals some C0 plus or even C0 because we have an external C0. So KC. Fine. This has sensitivity constant farads per volt. Fine. And now if in the LC oscillator so through lasso copy and I add in parallel to this. This is, oh sorry. This is the symbol for a varactor diode. I add a varactor diode in reverse bias. And let this be L0. Then and let this entire thing be C of, then C of Vi or C of T rather, then F naught L naught C of T. So the frequency of this oscillator is also a function of time. L naught C of T and C of T can be approximated as C naught plus KCV in KC in of T. C naught plus Kc this is within brackets 1 plus Kc. This beast fine. Equal to sorry F naught to 1 by 1 plus Kc V in T should be a function of T here. C naught to the power half. If Kc V in is much smaller than C naught, then Just let me call this FIT. FIT, yes. Phi T equals F naught plus Kc V in T divided by C naught of F naught. Fine. Equals F naught minus F naught Kc V in T by C naught. Fine. So this is approximately a voltage controlled oscillator and hence generates FM with the fine. Anything you would like to point out about this?
Sir, Vn
Yes.
is not controlled by us. It is output of the
V
oscillator.
no V in is not the output. V in it's the input, Bala.
That means
Input
we are
volt.
taking output from the RCs, right?
No, V in we apply here. We apply this V in to the varactor diode. Bala. Externally.
Then Vin is V out is across conductor.
V out is across. There is no V out actually. We are only interested in the frequency. But
The
yes.
output, output should be somewhere, right? So that means frequency should come out
Yeah.
from some.
Yeah. This you
Then
can.
Vin equal to V out.
How is V in equal to V out?
Both are connected by same wires. That means one end is directly connected and another end is direct.
So how do you take the see? I'm weak with circuits, so you'll have to help me here. How do you take the output of the oscillator?
I have a doubt that I don't know, sir.
Yes, I'm not so circuits is my weak point. Circuits and devices. So analog electronics is one of my weak points. I admit that. The point is that you're applying to this V in only across this V in is a reverse bias voltage applied only across the diode. So the circuit for V in is completed over here. That the circuit for V in is so this is the circuit for V in gets completed around the varactor diode, Bala. So this
Sir,
is
the Vin is same as VC, voltage across capacitor.
no, absolutely not.
They are connected by the same wire.
They are connected by there are two different circuits. Come on.
That means voltage across varactor diode is voltage across capacitor.
Voltage across varactor diode is voltage across capacitor. I disagree for now. I'll maybe pull up the book and look at the circuit diagram again. That is one thing I can do. So class materials, textbooks, and yeah, so it's downloading.
Sir, and again we are approximating k into v is far less than c.
Yes, we do
Then
that.
the bandwidth of frequency we will get will be very less.
Yeah, and that was the next point that I was coming to. But before that, let me look at the circuit diagram from the book. Maybe I'm missing something. No, this is the same thing that this guy draws. This is absolutely the same thing that this guy has drawn. Ah, I got it. No. Uh, yeah, so I'm kind of lost here, but because the book also has the same circuit, and as I have confessed, my knowledge of circuits and devices is fairly limited, and that of active circuits, op amps, etc., is absolutely pathetic. So
So the output of the frequency can also be taken via the current passing through the, which is also
yes, yes, Pavan, yes,
via,
it can be done. Thank you. You saved me. Thank you, Pavan. Yes. So Bala, that answers your question.
What, sir?
You can take the current, or you can take the frequency output via the
Then
current.
voltage, then also voltage and the current are interlinked. That means what inductor V in is
No.
same as.
That so that way, how do you operate any LC oscillator then?
The thing is,
Go
also
back
oscillator we don't have input, sir. We only
without
have.
any input. Is an LC oscillator a perennial source of does the LC oscillator defy the first law of thermodynamics?
Sir, my doubt
Bala,
is voltage across
Bala,
from this.
answer me first.
No,
Does
sir.
the
We use amplifier for sustain.
so amplifier is a voltage source, right?
Yes, sir.
Yeah, we use an amplifier here as well.
Here voltage across varactor diode is voltage across capacitor is voltage across inductor.
Go read yourself and explain it to me. I don't understand this. I'll be honest about that. I have no shame in admitting that this is my blind spot. I had a course on circuits in BTech. I managed to pass that. My master's is in communication. I haven't actually done circuits for the past 12 years now. So my knowledge is fairly limited and weak. So I don't leave this as an assignment question because I know the answers to assignment questions when I assign them. So this is not an assignment question, but yeah, this is a good question. I agree. And off the top of my head, I cannot answer this, but I'll look at it. You guys also look at it, and whoever finds the answer first, yeah, can share it with others. ज्ञान बांटने से बढ़ता है. But off the top of my head, you seem right, but there is something that I cannot put my finger on right now. So it's better we I spend some time thinking about it. They're not obvious to me. Yeah.
sir,
Yeah, Pawan.
Sir, I think for an LC oscillator, we generally first charge the capacitor and take
Yes,
out
we
the
need
V
to
input.
charge the capacitor. We take the output, and for an ideal LC oscillator, this is not an ideal LC oscillator as such. There's a diode, so yeah, I'm confused honestly. I never thought about this, and I took the picture in the book to its face value. So if you go to page 108 in chapter 3, I took the picture to its face value, and now I realize that as a circuit diagram that is incorrect when Bala pointed it out. The only way, because to me, the voltage the voltage across the varactor diode was never a part of the circuit. When I think about it, the voltage across the varactor diode is yes, that solves my problem. So this is a representative image. The voltage across the varactor diode is not a part of the circuit. That is one thing. How it is not made a part of the circuit, that is possibly Bala's question, or that is what would answer Bala's question. But yes, from what I understand now is that the voltage across, or the signal that we input to the varactor diode, is not a part of the overall circuit equation. How we separate that is possibly the question that we want answered. Am I right, Bala?
Yes, sir.
Yeah. So the question is not or the circuit as a circuit diagram. This is incorrect. What I have drawn. I agree. This is a representative diagram. That I understand. So how do we separate this voltage out? We need this voltage to control the capacitance, but I honestly do not know how will we separate this out of the circuit. Maybe you guys can check and see, because there are practical voltage controlled oscillators available in the market. They are available as ICs, and you can actually, if you come here for the next semester, we will actually work with, if you come here for the next semester and if I get to teach you the lab, then we will actually work with voltage controlled oscillators. The 555 timer is a voltage controlled oscillator in some sense. You know the 555 timer, guys? Have you seen, means in that instrumentation lab or analog circuits lab, have you come across the 555 timer? Okay. Yeah, so labs are slightly weak in the online mode. But the point is voltage controlled oscillators are possible, and I'll possibly have to read more to, means I don't know how and where to look, but I'll try my best. So Friday we'll answer the question, how do we get this? So this generates a narrowband signal, as Bala pointed out. How do we generate a wideband FM signal out of it? We'll try to answer on Friday. So we'll stop here now, and tutorial is Thursday 8 a.m. Okay, tutorial is Thursday 8 a.m. Please try out questions related to amplitude modulation, frequency modulation, and I'll try to answer those in the tutorial session. Okay, bye. Have a nice day, all of you.